Hello everyone, welcome to Chapter 4, Applications of Derivatives. And we continue with the lecture from last time into concavity and curve sketching. Let's start off with a definition for concavity. The graph of a differentiable function y equals f of x is concave up on an open interval I if f prime is increasing on I, and it's concave down on an open interval I if f prime is decreasing on I. Okay. Very straightforward looking definition. But a quick look at increasing and decreasing, because that's what we saw in the previous lecture. We saw that increasing and decreasing was for a function f. And for that, we said if f prime is positive, meaning the first derivative is positive, then it's increasing, the function is increasing. And if f prime is negative, then the function is decreasing. Here, we're talking about f prime, if that is increasing. So you need to take the derivative and then see if the derivative is increasing or decreasing. And so that's what will change the concavity here. Okay. As you can see in this graph here, which illustrates this idea of concavity, y equals x cubed is a cubic function. And as you can see, the blue graph depicts that function. And the portion of the function that appears in the first quadrant is concave up, because if you look at the derivative, right, f prime is the slope. The slope at every point on the graph, if that increases, if the slope increases, then you know it's concave up. And if you looked at the portion of the graph that's in the third quadrant, you can see that each time you take the derivative, the f prime decreases. And so that's concave down. A quick way to kind of understand the shape it takes, right? Because this is all about the shape it takes when you have f prime increasing and decreasing. You can now kind of cup your hands together and you will get a shape like this, isn't it? And if you keep the same shape, but then if you interchange your hands, then you will have the shape like this. So if you can form these kind of shapes, then you know it is concave up. And then it's like a smiley face, right? Yeah, you can see the up. You see the U shape formed in the up. So that's kind of easy there. And then if you had a frown, so invert your hands so that your fingertips touch each other, and so you now have the downward facing shape, and then again interchange them. It looks like this. So if it takes any of these shapes, you know that's going to be concave down. And again, this shape is all defined by the way f prime increases or decreases. Now it's all good if the graph is given to us, and we can definitely determine from the shape where it's concave up and concave down. But if you are given a function and not a graph, and you don't have a view of the graph, then we can do this, of course, using algebra and, of course, calculus concept of derivatives. And we say that if y equals f of x is twice differentiable, meaning you can differentiate it two times, first derivative and the second derivative, then we say if the second derivative is positive on I, the graph is concave up. And if the second derivative is negative on I, the graph is concave down. This is absolutely what the definition says, right? The definition says that if f prime is increasing, if f prime should increase, that means its derivative should be positive. Let me write that here. F prime increasing implies its derivative is positive. Where do I get this information from? This comes from the monotonic function, because for monotonic function we said if f is increasing, it implies its derivative is positive. And what is the derivative of f? F prime, right? So f prime was positive. So what is the derivative of f prime? That's going to be f double prime. The derivative of f is f prime. The derivative of f prime is f double prime. And that is what this second derivative test for concavity allows us to do. So if it is increasing, or it is concave up, right, where it's increasing, you know that you can use the visual to see if f prime is increasing, or you could use algebra and calculus concept of derivatives within it to see if f double prime is positive. Okay, we'll do some problems, of course, too, to figure this out. So I'm going to keep the same y equals x cubed. Let's look at the same graph, okay, and then we'll use that information to answer this first problem. So it says determine the concavity of y equals x cubed on negative infinity to 0 and 0 to infinity. Now we kind of gave away the answer to this, right? Negative infinity to 0 is concave down from the picture, and 0 to infinity is concave up. So we're going to show this or determine this concavity by using the second derivative test. Okay? So that's an alternative way to look at it. If you have the graph, you can see it, but if not, we're going to use the second derivative test. So the first let's write the equation and find the first derivative. That's going to be 3x squared. The second derivative, y double prime, is 6x. Okay. So now we have to see what happens to this x, because x is the variable. When x is negative, what happens? When x is negative or less than 0, it implies that y double prime, so 6 times a negative number will be negative, right? Y double prime will be negative, which means it's concave down when x is negative, which means concave down on negative infinity to 0, right? Those are all the negative values. And when x is positive, 6 times a positive number will be positive, so y double prime is positive, which makes it concave up from the second derivative test. And that's going to be for all positive numbers 0 to infinity. And why didn't we include 0? Again, remember, the definition is, this is the concavity test, but let's go back to the definition always. The definition is, it's concave up or concave down on an open interval I. And so it has to be always an open interval, because at 0, it's making that change. So we can't really tell if it's concave down or concave up at 0. In fact, there is a name for it too. We'll come to that. So we always have to write it as an open interval. And this is exactly what we saw in the picture. Concave down was for in the third quadrant for y equals x cubed, and concave up was in the first quadrant for y equals x cubed. Okay? Determine the concavity of y equals 3 plus sine x. And we're given the interval 0 to 2 pi. Okay, go back to the definition. The definition says the graph is of a differentiable function, so it must be differentiable. And then you'll talk about concavity. And then when you use the second derivative test, we know that y must be differentiable, but the test says it must be twice differentiable. And then we can consider its sign, positive or negative, to determine if it's concave up or down, respectively. Okay, so take the first derivative. We get 0 plus cosine x. Y double prime is negative sine x. It's a simple function, but you have that. Now we're focused on the second derivative. So again, consider what happens to x. Now remember, your x is values between 0 to 2 pi, right? So when x belongs to this interval. Remember, the E symbol means belongs. When x belongs to, I have to put open interval here because I want to look from 0 to pi, we notice that y double prime. So go ahead and pull out your calculator and plug in values. Pi is 3.14, right? So choose values less than that. So choose a test point and do a negative sign. What was it? 3, let's say, and make sure that it's in the radian mode. Okay. That comes out to be negative, which means it's concave down, and that's over that interval 0 to pi. And when x belongs to this interval, pi to 2 pi, okay, now this time it's 3.14 to 6.28, so choose a value in between. Say you can choose 5 maybe, and then see what that will give us. So that will give us, remember there's a minus here, right? So sign of a value between 0 to pi actually is positive, but with the negative in front of it, it becomes negative. And sign of any value between pi and 2 pi is actually a negative value. That combined with this negative makes it positive. So watch out for that. So it's concave up over that interval. So the idea here is, now if you compared your y equals 3 plus sine x, the y function, with the y double prime function, you will see that the concavity is more pronounced because of the places where it is negative and positive. So here's the picture for us. Eventually we'll be curve sketching, which means we will be sketching this blue graph. But right now I'm giving you the blue graph. You can use a graphing calculator to look at that blue graph. What you see is this top portion here. Let me just highlight it with, say, purple here. Just that portion. You see the shape there? The shape is like this. And we said that if it is, like downward facing, like a frown, we know that that's going to be concave down. And you know that that's concave down because of the corresponding y prime, which is all negative values, right? It's happening below the x-axis. So y double prime is negative. This negative information correspondingly means that your function is concave down. Okay. And then for the other portion, you see that? That is this up like feature. So you have the U shape forming there, and that correspondingly has this positive part, okay, where the y double prime is positive. Again, remember, after that, up to 2 pi, you have that information. After 2 pi, it goes down. So you're going to see it's going to be concave down again. But then we are only looking at the interval from 0 to 2 pi, and so you can see this behavior. And that's the reason why we really like the algebraic version of this, because you can actually use the information of the sign to determine if the curve will be concave up or concave down. Next question is to determine the concavity of y equals x squared. Okay. Again, this is a graph that you know, you're very familiar with this. It's a parabola that opens upwards. So y prime is 2x, y double prime is 2. So now question is, how does the sign change when we change x? Now in y double prime, there is no x. That means your y double prime is a constant. It's a number 2, no matter what your x is. Therefore, we know that this number 2 obviously is positive. Okay. And this is true for all, remember that symbol? For all x that belongs to the entire domain, right? No matter what your x is, for all x's, y double prime is positive. If y double prime is positive, it implies that it's concave up. Concave up where? Concave up everywhere. So what does it mean? That means when you draw the graph, right? Your graph will be always pointing up. Put that in. You see that U shape? It's a bad graph. See that U shape, when you cup your hands, that's the shape. So it's going to be concave up throughout. So we don't have y double prime changing in sign. And I have a better graph here. As you can see, y double prime is positive to the left of 0. It's also positive to the right of 0. It is true everywhere throughout the entire domain. And so that is why you have the U-shaped parabola for y equals x squared. So you can kind of, twist this question. What if it was y equals negative x squared? What's the concavity of y equals negative x squared? That's going to be concave down everywhere, because if it is y equals negative x squared, y prime will be negative 2x, y double prime will be negative 2. That's going to be less than 0, which means it's going to be concave down everywhere for all x. Yeah? All right. So, our next question then is, determine the concavity of y equals x power 5 over 3. You don't immediately remember or recall what the shape of this could be. So this is a good example for us then to understand the concavity from algebra. So y prime is 5 over 3 x power 5 over 3 minus 1, which is 2 over 3, isn't it? That's y prime. Y double prime will be 5 over 3 times 2 over 3 x power 2 over 3 minus 1. 10 over 9 x power negative 1/3. Y double prime will be 10 over 9 cube root of x. Now we need to see what happens for y double prime. Where does it change sign? But just before that, whenever you have this situation, you want to see where this becomes undefined, and we know this becomes undefined at 0. So x should not be 0, right? Meaning it implies that y double prime fails at x equals 0. This helps us to kind of break it up, to what happens to the left of 0 and what happens to the right of 0. So now let's say when x is negative, okay, what happens to y double prime? So choose a negative value, okay? Because it's a cube root, I just want to choose a convenient negative value. Let's say negative 27. This cube root of negative, is cube root of negative 27 defined? Or you can even choose a smaller number, negative 8. Is cube root of negative 8 defined? If you think about it, yes, because it's cube root, it will accept negative values because you'll be multiplying that number 3 times over, right? So cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 will give us negative 8. But it's not true for a square root. It is good for a cube root. When the root is odd, it works. It accepts negative radicands. Now, because of all that, we know that y double prime will be negative, right? Because that will be 10 over 9 is positive. So the only place where you can get a negative is out of this cube root of negative x value. So this implies concave down. And you know what the interval will be, because we said x is all negative numbers. So negative infinity to 0. Make it open interval, of course. And then when x is positive, y double prime, of course, will be positive. which is concave up, on this interval 0 to infinity. Yeah, if we want to sketch a graph, it's going to look like this. Something like this, okay? It looks like a cube or chair-shaped function, but it's not. Yeah. It's got some similarities, though. So here what we see is this portion here, right? We said this is concave down. And this portion here is concave up. So you got that. You notice something happens here. We said that at 0, right, y double prime fails. So something happens there, and that place where y double prime fails, which is the 0 position, the origin, that's called the point of inflection. So I'm going to define that shortly. The definition reads, a point C, f of C, where the graph of a function has a tangent line and where the concavity changes is a point of inflection. So where the concavity changes, so from concave down to concave up or concave up to concave down, when the concavity changes, that point is a point of inflection. No, so when you look at it from a graphical angle, you see that here this, you can see if there is a tangent at that point, and you can see if the concavity changes. Now, if we are looking at the function and we did the second derivative, then we can see it as a point where the second derivative becomes 0 or it fails to exist. And this is even more robust because you really can see that that's what's happening. Okay. So here we were able to see that y double prime fails because it became fails to exist, right? Because y double prime is undefined at x equals 0. So that was the point where it became undefined. In other words, y double prime fails, and that becomes the point of inflection. Consider the graph of y equals x power 4. Yeah. So y equals x power 4 is going to be like a parabola, but it's going to be really flat at 0. Now, what happens to the concavity? Think about it. Concavity, so this is a U-shaped graph, totally. So this is going to be concave up here as well as concave up here. Yeah, I can see that from the graph, but I can also verify that here. Y prime is 4x cubed. Y double prime is 12x squared. Okay. Because it's 12x squared, you know that when x is positive, take any positive number and square it. That's going to come back as positive. It means that y double prime of a positive number, 12 times a positive number, is positive, which makes it concave up. When x is negative, you plug in a negative number for x, and then when you square it, it becomes positive. So y double prime is going to be positive, which means it's concave up. However, y double prime will become 0, is equal to 0 when x is 0. So if you look at this definition here, at a point of inflection, either f double prime is 0 or it fails to exist. So that was an additional condition. We do have y double prime equal to 0 here. So is that a point of inflection? Is 0 a point of inflection? But if you go back to the definition, we always look at the definition. It says two things must happen. The graph must have a tangent line and where the concavity changes. So where the tangent line information is this, okay? F double prime is 0 or it fails to exist. Now that part is happening, but then the concavity did not change. So that is the reason why there will be no point of inflection. So let me clarify that here. Y double prime is equal to 0 at x equals 0, but the concavity does not change because it's concave up throughout. This implies we have no point of inflection. Okay, so make sure that both occurs at the same time. So now let's look at another example. Consider the graph of y equals x power 1 over 3. It's a good idea if you recall how the graph will look. It will look more like an S, because it's the flip of your y equals x cubed, right? This is the cube root. So it is the inverse function of that. So we have y equals x power 1 over 3, or cube root of x. Now look at this. What do you think about the concavity? Okay, there's a concavity, or rather, what is a concavity? To the left of 0 and to the right of 0. So y prime will be 1 over 3 x power 1 over 3 minus 1, which is 1 over 3 x power negative 2 over 3. So y prime is 1 over 3 x power. You know what? I'll just keep it as it is because it's going to be helpful for y double prime. So I'll keep it that. That's going to be 1 over 3 times negative 2 over 3. Y double prime will be 1 over 3 times negative 2 over 3 x power negative 2 over 3 minus 1. Negative 2 over 9 x power negative 5 over 3. So y double prime becomes negative 2 over 9 x power 5 over 3. Right? Move it down. If you want to see it a little more clearly, you can write this as cube root of x power 5. The reason I write it like this is to help me see if x can accept negative values or not, because when I see the cube root, you can see it in the fractional form too, but this is a little easier because an odd root will accept negative radicands. So we don't have a problem with negative values because this is not a square root, but we do see that this will become undefined when x is 0, right? So does the concavity change? Okay. When x is negative, you are going to get a negative quantity, negative x here, negative power 5, right? So negative power 5. So that also is going to come back as a negative. So cube root of a negative quantity will come back as a negative value, right? Therefore, y double prime will be negative of a negative quantity, which will make it positive, which implies concave up. And see the graph. The graph is concave up, right? It's got the upward look. And then x positive means x power 5 will also be positive. Cube root of a positive number will be positive. But this fraction has a negative sign, so y double prime will be negative, which implies it's concave down. So if you do see that concavity changes at 0, y double prime is undefined. I'll just say D and E. Y double prime does not exist or fails to exist at x equals 0, and the concavity changes. This implies there is a point of inflection at x equals 0. So coming back to the graph here, that's the point of inflection, because since there is a vertical tangent, right? This is when you look at the graph. When you look at the graph, you don't know that y double prime is undefined. But when you look at the vertical tangent, you know that that's happening there, right? For the first derivative, vertical tangent, and y double prime fails, and concavity changes. Let me put up the next problem. Determine the concavity and point of inflection for this function f of x equals x cubed minus 3x squared plus 2. Okay, let's find f prime of x. 3x squared minus 6x. And f double prime of x, 6x minus 6. So f double prime of x will be, again, plug in values for x to see what will happen. Okay, so when if you want the sign to be negative, right? If you want the sign to be negative, you want this 6x to be smaller than 6. If you want the sign to be positive, you want the 6x to be greater than 6. So keeping that in mind, what I would like to do is, by the side here, I'd like to set this second derivative to 0. So you get 6x equals 6, x equals 1. So 1 is the point where something changes, right? So, so I can say when x is less than 1, see what happens to f double prime. When x is less than 1, so choose some value less than 1. Okay, you can choose 0 because that's an easy one. So 6 times 0 is 0. 0 minus 6 is negative. So when x is less than 1, we get the y double prime is negative, which implies concave down on, and please write the interval because it's less than 1. So negative infinity all the way to 1. When x is greater than 1, f double prime of x, again greater than 1, try 2. 6 times 2 is 12. 12 minus 6 is 6, positive. So that's going to be positive. Choose a test point, right? That's going to be concave up on the interval 1 to infinity. Now, we need to see if we have a point of inflection, right, at 1. So we know that at 1, f double prime, okay, you just saw that, f double prime of x is 0 when x is equal to 1, and the concavity changes at x equals 1. It changes from concave down to concave up, which implies there is a point of inflection at x equals 1. Okay. So you can go further and find the coordinate for that. And this is how the graph will look. What we see is this portion here. You see that frown? You see that frown look? That means it's concave down. And this portion here is an upward look, U look. So that's concave up. And the point where it changes concavity, as well as where f double prime was 0, we have a point of inflection. In fact, you can find that point of inflection is when x is equal to 1, y is 1 cubed minus 3 times 1 squared plus 2. 1 minus 3 plus 2, negative 2 plus 2, which is 0. That's why this coordinate is 1, 0. So you can find the point as in a coordinate for the point of inflection. Here comes the next example. A particle is moving along a horizontal coordinate line, positive to the right, with position function s of t, 2t cubed minus 14t squared plus 22t minus 5t positive. Find the velocity and acceleration, describe the motion of the particle. Okay, t is greater than or equal to 0. So we're only looking at time from 0 positive onwards. We need to find the velocity. Velocity is denoted by v of t, but v of t is basically the first derivative of the position, isn't it? And so we need to take the derivative of s, which is 6t squared minus 28t plus 22. I know that I will need to factorize this because I will need that information later. So I'm going to do that right here. 2 times 3t squared minus 14t plus 11. Use the AC method or sometimes even the box method will work. Or you could just use the quadratic formula if you'd like. Ultimately, we want to get these factors. That will be 3t minus 11. Then they said find the acceleration. Acceleration is a of t, and we know acceleration is the derivative of the velocity. In other words, it's the second derivative of the position. So that will be, take this row here, 6t squared, that one, and take the derivative. So that's going to be 12t minus 28. Let's factorize this as well. So if you put out a 4, that will be 3t minus 7. Okay, the reason I had to factorize it because we need to get the critical points, and then we will talk about the behavior of S, then the concavity and all that. So we're going to do all that in this problem. Critical points are found by setting the first derivative to 0, right? Which means in this case, the first derivative is your velocity, and 2 times t minus 1 times 3t minus 11 equals 0. The factorized form will be so handy now because it implies that either t is 1 or t is 11 over 3. Solve for t. Now we can draw the number line and mark these points. Now remember our t, let me take you back quickly to the problem. T is greater than or equal to 0. So there is a starting point for t. So just moving it, I'm going to mark this as 0 so that I can accommodate the other values. Then we have 1 here and 11 over 3 here. These are the critical points. Critical points and end points are to be included. Here, end point is just the 0 end, not the, there's no end on the right end. So just mark that as infinity. All right, so we now have intervals 0 to 1, 1 to 11 over 3, and 11 over 3 to infinity. Sign of f prime, remember that? Here it is s prime, sign of s prime. So choose a test point here and plug it in s prime. So you're going to plug that in here. So between 0 and 1, you could choose a half. Okay, plug that in. And what you get is, let me just write here, s prime is the same as v of t. Okay, so you know where you're plugging it in. You get positive, you get negative, and positive. So positive means it's increasing, decreasing, increasing. That's the behavior, okay? The behavior of S, or the particle, is that because we're talking about velocity, right? Increasing, decreasing is the behavior of it as a graph. But when you talk about the particle moving and the velocity, that considering it, velocity is positive or negative depending on right or left, okay? So then because the particle is moving, let me take it back here. It's moving along the horizontal coordinate line, positive to the right. That's the direction it's moving. That will be the positive direction. So if it is moving against that direction, that will be the negative. Therefore, because it's already moving in the right direction, if it's negative, it has to be moving in the left direction. So I come back here and say, this would mean, positive would mean right. The particle is moving right. Okay. You know what? Bear with me, please. I'm going to write that information here below. Increasing, decreasing, increasing. And I'll say particle motion. That way I can write it as right, left, and right. So now we'll also consider the sign of the second derivative, okay, because that will help us with the concavity. Sign of S double prime. For our convenience, S double prime is nothing but the acceleration, right? So the sign of S double prime was, for that we need to consider, let's come over here, the second derivatives equation and set that equal to 0, because that's where we'll know where the sign changes. So S double prime equal to which implies 4 times 3t minus 7, set it equal to 0, which implies t is 7 over 3. So you want to separate or split up your number line between the left of 7 over 3 and to the right of 7 over 3. But here again, I can't go all the way to negative infinity. So I'm going to keep the starting point as 0, right? Because that won't change. So then now my intervals would be 0 to 7 over 3 and 7 over 3 to infinity. And so then now I'd write the sign of S double prime. The sign here will be negative. The sign here will be positive. Take a test point again and plug it in the second derivative. You get that. And then we have concavity. Because it's negative, it's going to be concave down. Second derivative negative is concave down. Positive is concave up. Wonderful. Now we're going to hash all these things together to sketch our curve. Okay. Sketching the curve. How do I know we should be sketching the curve? It didn't say that. Well, it kind of did. It said describe the motion of the particle. Okay, we just said left and right, but we want to give the motion of the particle. To describe that graphically, we need to sketch the given graph. So go ahead and draw your axes with all these points. Like you need to have 0, there's 1, 7 over 3, 11 over 3. Put them all together. So get something like this. If it helps, you can always get the decimal equivalent. This is 2.33. This is 3.67. That way you know where to position them and which comes first and which comes. Well, they have the same denominator. So, it's kind of easy because it's lined up. 1 is 3 over 3. So 3, 7, and 11. So you have that. Now we need to look at these points. We know 1 and 11 over 3. These were the places where we had, let me take you here quickly. Those were the critical points, 1 and 11 over 3. That means that's where you'll have a horizontal tangent, right? Horizontal tangent. Now we have from 0 to 1, it's increasing, right? The function is increasing because that's what we determined here. The particle is moving right. Okay? Function is increasing. And for the second derivative, right, 0 to 7 over 3, it's concave down. So I'm going to erase this right after I write this, otherwise it'll get cluttered. In this interval, it's concave down. But in this split here, 0 to 1, it's increasing. And let's come back here. And 1 to 11 over 3, it's decreasing. Sorry. And here it's decreasing. Oh, 1 to 11 over 3. Okay. All the way here. Decreasing. That means it is decreasing in this portion as well, right? And it continues to decrease here. And then we come back here. 11 over 3 to infinity, it's increasing. So this part, it's increasing. However, we come back here. From 7 over 3 to infinity, this part is concave out. So you have all these details in here. Okay. Perhaps we could hold on to this and then we could, sketch another one, draw another grid. You can do that. Or you can capture this information and then erase it and draw over it. It's your choice. So if it's increasing and decreasing and it's concave down, remember concave down has this shape, right? It's either like this or it is switched like this. So now if it's increasing from left to right, it should rise, right? So this is the portion for increasing and this is the portion for decreasing. So I'm going to keep that information here. I just want to sketch over this. Okay, that's 1. And then from 1 down, it's decreasing. Yeah. And I know it has to make that smooth turn there because that's where the horizontal tangent is, or the first derivative is 0 at 1. So I've got that part. So we got the concave down, increasing, decreasing, this portion taken care of. Okay, good. Next we have concave up. Concave up. So it has to look like this. Or it has to look like this. Concave up, first it's decreasing. Okay, so it has to fall. And then it has to increase. Okay. But it's concave up throughout. So decrease is this, because from left to right, if you look at this graph from left to right, it's falling. And then that's decreasing. And then from 11 to 3, it's increasing. But both are pieces of the concave up. So you know that this has to go down. But at 11 over 3, it has to make the turn because that's where you have the horizontal tangent line. And then it's increasing. And again, clean all this up. And that's how we sketch the graph. Well, to make it a little more pronounced, you have to go to this 1 and in your S function, find what S of 1 is. S of 1, plug it in. The function was 2 times 1 cubed minus 14 times 1 squared plus 22 times 1 minus 5. This whole thing comes back as 5. So this will be 1, 5. So this has to be, well, you have to get your scale accordingly, of course, right? 1, 5. And then here again, 11 over 3, find what S of 11 over 3 is. And when you compute that, get negative 13.96. So again, my scale is really bad here because this has to go all the way down, further down, because this is 5 here and this will be a negative 13. Okay, so that's a disclaimer I have here, that this point will be 11 over 3, comma, negative 13.96, because it's a little bit, a decimal value. And in fact, you can also find what happens at 7 over 3 so that you can graph it. 7 over 3 will correspond to negative 10 point something. Anyways, you've sketched the graph here, and this is S of t equals 2t cubed minus 14t squared plus 22t minus 5. And I want to say that this is increasing, decreasing, concave down, concave down. And then this portion again was decreasing, concave up. This portion was increasing, and this was concave up. And that's really interesting because of that, because of all those things that we noticed. And with concave down and then concave up, things changed, right? So we do have. Well, I made this. I made one error though. I made this 7 over this graph pass through 7/3. It wouldn't pass through 7/3. It's going to pass through somewhere else, right? Because it's it went to decreasing all the way to 11/3. So just to fix that, I'm going to mark this somewhere here, 7/3. All right. Because at 7/3, it's not 0. That's what I'm trying to say, okay? Because if it's going to pass through the 7/3 on the x-axis, that means s of 7/3 must be 0. That's not the case. Then s of 7/3 gives me negative 10.67. Let me write that. So it's definitely not passing through 7/3. All right, so that's our sketch here. Now we have a second derivative test for local extrema. Okay, so this is different from the other second derivative test because the other one was second derivative test for concavity. This one is for local extrema. Okay, so is there a local max or a local min? That's the stuff. Suppose f double prime is continuous on an open interval that contains x equals c. If f prime of c is 0 and f double prime of c is negative, then f has a local max at c. If f prime of c is 0 and f double prime is positive, then it has a local max, local min at c. If it is if the first derivative is 0 and the second derivative is 0, then the test fails. The function may have a local max, a local min, or neither. If the test fails, you really can't conclude, right? It's inconclusive. So that's what we're trying to see here. Now, if we have f prime that is in each of these cases, f prime is 0, right? Meaning at the critical point, you're trying to see if the second derivative is positive or negative. Okay, so we'll do a problem and understand this. Sketch a graph of the function f of x equals x power 4 minus 4x cubed plus 10 using the following steps. A. Identify where the extrema of f occur. B. Find the intervals on which f is increasing and where it's decreasing. C. Where the graph is concave up and concave down. D. The general shape of the graph. And E. Plot some specific points such as local max, min, points of inflection, intercepts, and so on, and then sketch the curve. All right. Now, before we begin, we need to check the premise, isn't it? So let's do that first. The function f of x, we know, is a polynomial. It's actually a polynomial of degree 4. This implies f is continuous, actually everywhere, because there is no restriction on the domain. But if you look at the entire domain, we have still no problem because it's a polynomial. If it's continuous, then it really helps us to see that that premise is satisfied. And then we need to consider the, I'll also say no endpoints. Yeah. This implies critical points. Critical points are the endpoints and the derivative, first derivative to 0, where f prime of x equals 0. Let me understand these things. So I'll do the first derivative of x. Oh, let me write f of x first because it's somewhere up in the problem. X power 4 minus 4x cubed plus 10. F prime of x is 4x cubed minus 12x squared. It's called plus 0. 4x cubed minus 12x squared. F prime of x equals 0 implies that you set this to 0. Suppose, remember the drill, that when it comes to polynomials, we always factorize them. So we have 4 and the x squared, that's the GCF. That gives us x minus 3 equals 0. This implies set this x squared also to 0. That means x is 0 or x equals 3. Now we draw the number line. Because there are no endpoints, I mark the ends of the line as infinity, negative infinity, then I mark the 0 and the 3. So the intervals would be negative infinity to 0, 0 to 3, 3 to infinity. Sign of f prime. Choose a test point from negative infinity to 0. You could choose negative 1 perhaps, and plug that in your f prime. Okay, 4 times negative 1 the whole cubed minus 12 times negative 1 the whole squared. And that comes out to be negative. Choose a test point from here as well. I choose 1. So 4 times 1 cubed minus 12 times 1. So 4 minus 12, negative. And then choose some point from here. Let's say 5 or even 4. And that comes out as positive. Then behavior of f will be decreasing, decreasing, increasing. I guess we have enough details to answer part A and part B, okay, because of the extrema and increasing, decreasing. Okay, for extrema, you will use the first derivative test. Okay, what happens is we have the negative. Okay, the only place where your sign changes, right? The sign of the first derivative, where it changes is at 3 from negative to positive. Okay, that's the only place where it changes. Therefore, and from negative to positive, the first derivative changes from negative to positive. We know that there is a local minimum. Implies local minimum at x equals 3. F prime changes from negative to positive. That was the reason for that. And then for part B, where it's increasing, decreasing, we know it's decreasing consecutively. So the function f is decreasing on negative infinity to 3 on this interval, okay, all the way to 3. I don't have to put it as negative infinity to 0, union 0 to 3. It's all the way, and increasing on 3 to infinity. Okay, and part C, says to find the concavity. For concavity, we need the second derivative. So for convenience, I'm going to write the first derivative here. 4x cubed minus 12x squared. So now if we find the second derivative, that will be 12x squared minus 24x. Of course, we need to set the second derivative to 0 to know where the concavity will change, if it changes. Once again, factorize it. So 12x can be pulled out, x minus 2 equals 0. This implies x is 0, or this x minus 2 is 0, which is x equals 2. Now for this, you'll have to draw the number line and decide how the concavity changes. Negative infinity to 0, 0 to 2, and 2 to infinity. Sine of f double prime. Choose a test point and plug it in this 12x squared minus 24x in that expression. So if it's a negative 1, it's 12 times negative 1 the whole squared minus 24 times negative 1. Yeah. That's going to be positive, negative, and positive. When you do the test points, and then you have the behavior of f. The behavior of f will be that this is positive, so it's going to be concave up, concave down, and concave up. That's your C. Too far. That's your C. D is sketch the general shape of the graph for f. Okay. A general shape, they said, not the complete curve. So let's summarize all of the ones that we did above. Summarizing A through C, this is how our graph will look. These are the shapes. So we got a 0, then there is 2 from the concavity graph here, right? And then there was a 3 from the other one. So I'm going to put all these numbers here and begin to look at what happens. Okay, so 0, negative infinity to 0. Here it's concave up. Negative infinity to 0. 0 was decreasing and concave up. So I'm going to compile all these details here. Okay. Decreasing and concave up. 0 to 2. 0 to 2 is concave down. But here it's 0 to 3. 2 is somewhere in between. But so 0 to 3 is decreasing. So 0 to 2 must also be decreasing. So decreasing and concave down. Okay. So because I'm color coding them, and I'll just do that so that the interval is indicated indirectly there. And 2 to 3, we just saw that that will be decreasing again because it was decreasing from 0 to 3. Okay. And 2 to 3. So 2 to infinity is concave up, which means 2 to 3 is also concave up. And then 3 to infinity will be concave up right here. And from here, 3 to infinity is increasing and concave up, the last one. if we consider the general shape, decreasing and concave up, this is the only piece that will be decreasing and yet concave up. Decreasing and concave down would be this piece, right? Use your hands to kind of pick up the shape. Decreasing and concave up, same as the first one. Increasing and concave up must be the other part of your concave up. So now this is what we have. And what we also see is at 0, 2, and 3, right? That's where it breaks up. I want to see with because the concavity change here and because your second derivative is 0, because of second derivative 0 and concavity change, we have point of inflection. Let's come here. Concavity down to concavity up, and the second derivative was also 0 there, right? 0 and 2. Concavity changes. Point of inflection. Concave up, no point of inflection there, but we did determine that there was a local min from part A. So now we have all these details together. If you put them all together, this is how the general sketch will look. Okay, so that's negative infinity all the way to 0. You can see that. Okay, this point, find the coordinates, of course. At the 0, 10 inflection point. Then we have 2. 2 also has an inflection point. So that will be 2, negative 6 when you do the coordinates. That's an inflection point. And then we had 3, negative 17. That was our local min. Okay, because of the setup, it appears that that must also be the absolute min. And so we got all our shape kind of matched there. So you see this portion here. So 1, 2, 3, 4. So we have the 4 parts here all brought together. And that was, of course, part E. What I'd like to do now is give you a quick recap of all the theorems we've seen so far. Okay, so it will be a nice place for you to kind of see them all coming together. So remember EVT, extreme value theorem. So what it said was F is continuous, which if F is continuous, then it implies that both absolute max, of course, continues on AB, closed interval. Absolute min exists. I'm not trying to rewrite the entire theorem. I'm just trying to recall what we did in those theorems. Okay? And then we had the first derivative theorem, because there's also a first derivative test. First derivative theorem says F has local extrema. If F has local extrema at x equals c, it implies F prime of c is 0. And what are the places where you'll find the possible extrema? We'll find them in the interior, of AB, where F prime C is 0. You could find it in the interior, where F prime is undefined. And you can find it in the endpoints. If there are no endpoints, then the critical points are just used. Okay. Then we saw Rolle's theorem. Rowe's theorem was something like this, right? Think of the M setup. And let's say A and B and f of A equals f of B. Then we said we can find horizontal tangents there, right? So I'm not going to write that information, but we know that these were the places we found f prime to be 0. Whatever those positions were, right? C1, C2, C3, say. Then we found, we looked at mean value theorem, MVT. And that said if f is continuous on AB and differentiable on the interior of AB, then f of B minus f of A. Slope of the secant line was the same as the slope of the tangent line. Or in other words, average rate of change between A and B was equal to the instantaneous rate of change at C. And then based on MVT, we had some corollary. Corollary 1 said f prime of x equals 0 implies f of x must be constant. If the derivative is 0, then throughout, if the first derivative is 0 throughout the graph for all x's, the only way it's possible is if it was a horizontal line. Then corollary 2 stated that if we have two functions and if their derivatives are the same, meaning their slopes are the same, the only possibility is that these two are parallel to each other. So f of x equals g of x plus a constant so that they are separated from each other. Corollary 3 stated that if f is continuous and differentiable, so that basically corollary 3 was your monotonic function, the definition of a monotonic function. Then f is increasing, f is decreasing. Then we had the first derivative test. Right? Remember, the first one was a theorem. So I will take you back here quickly. This is first derivative theorem up here. Down here is first derivative test. C is a critical point. If C is a critical point, and if your first derivative changes sign from negative to positive, it means f has local min. If f prime changed from positive to negative, it implies f has local max. And if f prime had no change, f has no local extrema. That was your first derivative test. Second derivative test, we have two things. We have second derivative test for concavity and we have one for local extrema. So second derivative test for concavity. This one said f double prime, if it's positive, it's concave up. Concave down. Then we'll also quickly define critical point. So defined it way back, but that's okay. Critical point is where f prime of C is 0 or f prime of C is undefined. Well, we needed that right way in the beginning. But we also saw a point of inflection. Okay, concavity changes, and you have this condition fails to exist. Okay, so you want both of them to happen. So you want to really investigate. Don't just go by just the F double prime situation. Then we have second derivative test. This time it is called local extrema, the one that we just saw. And this one says F prime of C equals 0 and F double prime of C negative. It implies local max. F prime. So it's basically combining the first derivative and the second derivative. It's positive. Local min. Okay. So 0 and concave out. If both are 0, test fails. When test fails, the test is inconclusive, which means there may or may not be local max or local min. Okay. So this was a collection of all the tests and theorems that we've seen that leads us to sketching a graph. So thank you, class. That concludes our lecture here. I will see you in the next video. Bye.